Ever since last week, you've been hearing me say this word distribution. Just for the sake of understanding, let me just, in parentheses, you have this title on your notes now. In parentheses, go ahead and write data that's presented. Data presented is what distribution means. Data presented. And what I mean by presented, I mean in an organized way. For instance, okay. Here's what I mean by data presented. How many siblings do you have, Mr. Boston? How about you, Mr. Rosas? 4. Ayala, how many siblings? 5. And Castro? 2. Pinello? Rodriguez? 3. Juarez? Ortiz? 3. I have 2. Now, in front of you is just raw, what we call raw data. Just numbers separated by commas. It's just raw data. It's not presented and it's not organized in any way to let a scientist know, a researcher know some of the behaviors of the data, some of the interesting characteristics or features of the data. It's just raw numbers separated by commas. But if I were to make, watch this now, don't write this down, just pay attention. If I were to make a box plot of the data, then at that point, I've organized the data in such a way where it tells me a story, it gives me the important characteristics. This is called a distribution. Okay? It's data that's presented in an organized way, in like a graph or something. The other one we went over last week, and you had to do this on the quiz. You don't have to write this down right now.
Not even the numbers?
No, nothing. If I made a histogram of this data, I'm just making this up, this would be a distribution. So it's data that's not raw, but has been organized for us to see and behold and study, like in a graph. That's all distribution means. It's a fancy word. Now we can pick up our pens, and let's review what we did last week. Watch this. One type of distribution that we did last week, we'll draw a vertical axis and a horizontal axis. And just give me 5 bars that are like staircases going down. Go and do that for me, 5 of them. It doesn't have to be fancy schmancy Picasso artistry. Now, if we're to idealize this histogram and connect the tops of the bars with a curve, it would look like this. So next to it, go to right. So all the data, all the bars are kind of like the curve. The curve is like an idealized way of portraying the shape of the distribution. What would be the shape of this distribution we learned last week? How would we describe the shape? You guys remember? Skew to the right. So the tail, okay, here's a tail, right? This is the tail. If it's on the right, then we say this data is skewed to the right. I'm going to write this down. Skewed right, the data. So right now it's kind of review. Let's do another histogram underneath. Let's do the 5 bars going down this way. 2, 3, 4, 5. Let's form an idealized curve of those bars. It'll look like this. Obviously, this would be skewed left. Skewed left. So far, so good. One, two, three, four, five. So what would the curve look like now? Watch this. It would look like this. The curve would somewhat look like that. So this would be symmetric from last week. The right and the left side are kind of the same. Symmetric. Now, Yellow, what's the title of our notes? Normal. Notice, normal. I'm introducing a word called normal. Out of the three, skewed left, skewed right, or symmetric, what do you suppose would be the normal one? Symmetric. So another word for symmetric now, and you'll see this when you get to college, is what we call a normal distribution. Go to write normal. It's a synonym or AKA. Symmetric and normal mean the same thing in statistics. When data is organized and it creates that shape, a normal distribution, all kinds of fireworks go off. All kinds of special things happen in terms of us predicting what the data can do. There's like normal patterns of what the data communicates to the observer or to the scientist. This is a very, 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 very special shape. If the data creates this shape, how special things happen. Sometimes it's called the bell-shaped curve. We call it a bell curve. Go write that in your notes. Because it looks like a bell. Okay? Fireworks go off when you have data that looks like this. That's what we're going to delve into right now, just to start off with for today, and we're going to continue tomorrow. When you have a bell-shaped curve, or another way to say it, a normal curve, or another way to say it, a symmetrical curve, here's the fireworks now. And we'll end our notes with this. Go ahead and write the 99, or actually the 68, 95, 99.7 rule. I'm going to write that down. So it's like a subsection of your notes here. The 68, 95, 99.7 rule. And notice I got a normal distribution right here, and there's certain parts of it being shaded. That's where we're headed. That's where we're headed tomorrow. But for now, I'm going to write that down. So, special things happen. Fireworks go off. The fireworks that go off, if you have a normal distribution, have to do with these numbers. Okay? But before I tell you what those numbers mean, why the number out of all the numbers, why 68, 95, 90, what the heck is that? Give me a second. Let me set you up for this. Go ahead and draw a nice big, so take up a good part of your paper now, underneath this subtitle. Give me a nice big, what? What was that? That was scary. Who said that? Is that like the math ghost or something? Phantom? Oh, okay. That's scary. Here we go. Give me a nice normal curve. Here we go. Nice and big, like that. Yeah, it takes some practice. If it's jacked up, don't worry. It'll take practice. The 68, 95, 99.7 rule. All right. From last weekend, there was actually a quiz question on this from Friday. On the way right now, yellow. What is the best way to measure the center if the data is symmetric like this? Would it be the median or the mean? Median would be if it's skewed. So it'd be the mean. So now, with your nice, smooth, symmetrical curve, right down the middle, draw a line, and go ahead and put mean right here. The mean will always be the middle value. If your distribution is normal, remember normal, I mean symmetric, the mean will always be in the middle. Do you guys remember the weird, funky variable that meant mean from about 3 weeks ago I introduced you to? There's a variable that always means the mean. Kind of weird to say it that way. It always means the mean. What's that variable? Nice. X bar. You're the man, Pinello. X bar. All right. You guys are seniors on your way to Chaffee or Mount Sac or some other college. X bar is actually for kiddies now. For higher level statistics, the mean is designated by a different variable than X bar, and it's actually another Greek letter. I apologize. So this is for kiddie stuff now. So go to underneath X bar, going to put or. We're going to start using this one now. Ready? It's a Greek letter called mu, with an M as in Mary. Mu. Sounds like new shoes or new pants or new car, but instead of the N as in Nancy, it's mu, and it looks like this. It's like a U, but the line right here is a little longer than this one. Yes. He's like, what? So the way to say this is mu. This is how you say it. Mu. It's a Greek letter. Let me draw it a little bit bigger. It's like a line, a U shape, and then this one's a little bit smaller. So this line is a lot bigger than the one on the right.
Why is that?
It's just a letter in Greek. It's like asking why is a lowercase t that smaller. It's just the way the Greeks made their language. So the Greek variable now is mu. Like rhymes with new, but it's mu. Mu is going to designate the mean. No more X bar. That's kiddie stuff. You guys are seniors. You guys are on your way to college. We're playing the big leagues now. So here we go. So we got the mu, which is your mean. You guys remember what was the funky Greek letter? I can stop, Mr. Rodriguez. Go ahead.
No, that's okay. I'm just going to pass out some stuff.
All right, ready, Rosas?
All right.
What was the Greek letter that designated standard deviation?
I don't know.
Wada, say the day. Sigma. So watch this now. Standard deviation was designated by the sigma symbol. Here's what we're going to do with your curve now. Watch this. Here we go. Where the curve changes direction. So right now the curve is going down. My bad here. Notice on the right side of the curve, it's going down and it changes direction right about right there. From going down to going left, that point right there where it changes direction is going down and it starts going left. That point on the right, that point on the left, go ahead and plot a point the way I did on your picture. There's a very special point on that curve. So notice, it's kind of like the point where the curve goes down and it starts changing from going down to going left. It's a very, very important point called a point of inflection. I'm not going to hold you to that word. But that's a very special point, and here's what I want you to do at that point. I want to draw another line coming down. There. Another line coming down here. Notice how, look at this picture here, this animated GIF picture. Look at how sometimes it's shaded at the point of inflection on. below and above the curve. So that's the point of inflection. It changes direction from going down to going to the left. Okay? Now, what is that first point? Check this out. If the mean is right here in the middle, then at that point of inflection is your first standard deviation above the mean. So we're going to put sigma there. Tomorrow we're going to review how to find the standard deviation again. But that's sigma. That's one standard deviation above the mean. It's always at that point of inflection where that curve changes. It's always going to be right there, the first standard deviation. And below it will be the first standard deviation below the mean. So put minus sigma. So you have the mean. To get to this first point of inflection, what the data value is, you just subtracted one standard deviation from whatever the mean is. And we're going to get into this more tomorrow. Right now I'm just giving you the parts. Don't get stressed out too much. But do stress a little bit. It's always healthy to stress out a little bit. Makes you stronger. Tighten that up. All right. Watch this now. The same distance, I'm going to just like eyeball it. The same distance from here to here, from the mean to the first standard deviation below, about the same distance, I'm going to put another line there. And do the same thing on the right side. About the same distance, another line. So that second line above the mean is actually 2 sigmas. 2 standard deviations above. And the second line below is negative 2 sigmas, negative 2 standard deviations below. Again, we're going to review what standard deviation means tomorrow. You are aware of it, though. The 2 quizzes ago, you're able to manually find the standard deviation of data. Remember those 4 columns, those time-consuming, you guys were stressed out? Well, I showed you how to find it quickly with a calculator. We're going to review that tomorrow. So you're no stranger to standard deviation. All this means is if your mean is here, positive standard deviation above, 2 standard deviations above, and there's one more now. Put a third one. This would be 3 standard deviations. 3 sigma and minus 3 sigma. So far, so good. So we got mu, that's the mean, mu in the middle. 3 standard deviations above, 3 standard deviations below. Tomorrow, I'm going to get into what the 68, 95, and 99.7% numbers mean. What the heck does this mean? It has a lot to do with this little GIF that you're looking at, this picture. Okay? So right now, you're going to go ahead and grab your Chromebook. You're going to do a credit check. You're going to save your notes. You're not going to lose your notes.